Hi, we are As Above, So Below Foundation Monitoring System. In this video, we'll walk through our project overview, process, meeting the team, results, and reflections. Let's get into it. Our system reads foundation movement at each sensor node, sends the data wirelessly to the MCU, and then to the main hub where filtering and logging occur. The process results are displayed in the UI, which alerts homeowners to any significant movement.
Our system helps reduce stress for homeowners by detecting early movement and preventing structural damage and costly repairs that follow. Our goal was to design a real-time foundation movement monitoring system using multiple sensors, custom PCBs, wireless communication, and full data processing and UI pipeline. The system tracks millimeter-scale foundational movement.
Here's our process. We began with research, with each team member focusing on their subsystem and chosen sensor. Then we moved into hardware development, integrating sensors into a node and designing the PCB. The node sends data wirelessly to our Raspberry Pi gateway, where filtering and ML improve accuracy. The process data goes to the UI for visualization and homeowner alerts. Finally, we verified the full system using custom test rigs and simulation platforms. Let's meet the team that made this process happen. Sloan served as our project manager and led the data processing subsystem. Will focused on hardware development, Orlando worked on data acquisition, and Cassidy worked on the user interface system and testing simulations.
Hi, I'm Will with hardware development. This is the overall block diagram for our sensor nodes, which revolves around an ESP32C6 microcontroller. Inputs from the sensors can be seen on the left with outputs on the right. There were 3 total iterations of our PCB throughout the semester, with small changes in between that mirrored our shift in focus on particular sensors. Here you can see our final iteration. A test was conducted between 2 similar nodes in order to ensure repeatability in measurements. Data was captured from the IMUs for 60 seconds and their measurements analyzed. Overall, there was great repeatability between measurements with a mean standard deviation of 0.02.
Hi, I'm Orlando with data acquisition. This block diagram shows general data flow for our data acquisition process, where a microprocessor is configured to try and connect to our designated Pi broker for data processing and logging. On the PC side, the broker responds to the subscriber, ensuring it receives the correct published data, either for logging or for visuals. We tested 6 sensor nodes transmitting at once to measure latency and packet reliability. The system kept 99% of packets with virtually no losses, even without monitoring. This confirmed the network can handle multi-sensor streaming.
Hi, I'm Sloan with data processing. This system takes sensor data as input into a Jupyter notebook, and if the dataset is uncorrupted, measurement-specific plots are generated for visualization and logged into a research document. Those logged plots take 2 different paths. Let's start with filtering. Various filters are applied to the data and then visualized and logged into our research document. If it takes the machine learning path, a correlation matrix is generated, the data is then split into train and test data, and linear regression models are applied. These data outputs are logged and compared with the filtering outputs. Here are some of those plots on our radar. As you can see here, this is a dynamic test where the radar is moving closer to the sensor, and we have raw versus each type of filter. Then here is a static test where you see raw versus filtered. To ensure that the filters are working properly in Jupyter Notebook and in our Arduino code, there are 3 different test runs on our time-of-flight sensor. The middle column shows the correlation, and the right column shows the root squared mean error. The correlation is as close to 1 as possible, and they are both pretty similar, so these are really good results overall. Here's that comparison, where you can see the Python code versus the Arduino code for each of the filters. Overall results. All 3 tests passed with flying colors.
Hi, I'm Cassidy. I was responsible for the user interface. I designed a desktop UI with mobile phone push notification alerting. This block diagram shows how the UI pulls data from the server. The results: blueprint-style floor plans and sensor-specific pages that show live data, color-coded movement indicators, and historical graphs. I measured the end-to-end delay from sensor output to UI update, and the system averaged about 0.5 seconds, which is well within real-time monitoring limits. Moving on to testing and simulation, I upgraded our testing rigs from a basic linear setup to a modular tilt and linear platform. This let us simulate both displacement changes and small angle movement for all sensors. I ran 10 one-hour accuracy tests on the server-controlled linear displacement platform. Across all runs, the system held an average error of only 0.05%, confirming the platform is precise enough for long-term sensor evaluation. As you can see, the expected distance was only 0.005 millimeters off.
Now let's go to our overall results. Here are the sensors. Initially in Design 1, we explored a multitude of IMU sensors, force sensors, soil moisture, and time of flight. Ultimately, we went with one 9-degree of freedom IMU and one time of flight sensor. We also explored 3 other sensors in Design 2. However, we decided that the radar, the time of flight, and the IMU were the only ones to explore for this semester.
Here you can see the results for the B055 IMU we tested in a static environment, with the X, Y, and Z readings shown on a time series plot. Here you can see the scatter plot for that same static test, giving us a 3D visualization of our results. Another feature this B055 supports is outputting in quaternions. Since this is a static test, we're expecting values near 0. Again, you can see the correlating data for our previous slide here in 3D space. Although the sensor is relatively accurate, you can see it exhibits too much drift for our use case.
Our next sensor is the time of flight. For this sensor, we ran 10 1-hour tests and one 10-hour test, each using a 1 centimeter controlled displacement. Across all trials, the time of flight showed about 2% error with a 0.6 millimeter standard deviation, giving us a clear picture of its precision and accuracy.
Our final promising sensor is the radar. It has about a plus or minus 2 millimeter deviation. And once filters are applied to it, it becomes even more precise.
We compared sensor accuracy, cost, power requirements, and ease of integration. This analysis informed our recommended sensor fusion approach. Radar came out on top with time of flight trailing less than 2% behind.
For our project requirements, everything passed with flying colors except for achieving within 1 millimeter of accuracy. We did, however, achieve within plus or minus 5 millimeters.
Now let's take some time to reflect. For challenges, we faced IMU drift of about 0.5 millimeter per day, tight time constraints, and the complexity of converting our Python filtering into embedded code. For the next group, we recommend focusing on multi-sensor fusion using radar time of flight IMU, expanding the machine learning filtering across all sensors, as well completing the differential pressure sensor testing.
And here is our proposed sensor fusion. With the time of flights working in a liquid level system, the radars doing motion detection, and IMUs as a secondary backup. We want to say thank you to our sponsors, SATOP, Texas State, Stable Options, because you guys are the foundation of this project.